Welcome viewers to the 19th lecture on the open online course Computer Numerical Control of Machine Tools and Processes. So, today we will have the concluding lecture on cutter path generation for machining freeform surfaces, and in the remaining time we will discuss some of the current trends in this particular area. To start with, we have already finished the discussion on iso parametric machining and iso planar machining. We have discussed in detail the forward step calculation for iso planar machining, and today we will be taking up the last part, iso scallop machining, which produces equal height of roughness scallops all through the surface. So, scallop height is kept constant, which leads to uniform surface roughness. This requires less machining time because there is no redundant machining. Secondary cutter paths are derived from a master cutter path, and the master cutter path is generally taken to be one of the edges of the surface. So, this shows two positions of the tool along two adjacent cutter paths, and this is the material which is left over uncut, and this height is called the scallop height. So, this is just a reminder, we have gone through these expressions before. These are the derivatives. For example, the derivative of the surface in the u direction dot producted with itself gives a particular value which is equated to E, that is, it is given a name E. F is the dot product of R u dot R v, G is the dot product of R w dot R w, etc. These things we have discussed last day. This is the expression of the curvature, which is taken to be 1 by R in this case, and it contains all those constants which have been defined previously, like L, M, N and E, F, G. Together with that, we have a du dt and dw dt multiplier, which can also be simplified to du by dw, and this varies with the direction in which we are considering the curvature. For a freeform surface which is curved, the curvature might be different in different directions, while L, M, N, E, F, G, they are invariant with the direction. Du dt and dw dt or du by dw, this varies with the direction, and this is the first fundamental form of the surface. We will come across this very soon. In isoscallop machining, in this particular publication, the forward step was found out without iterations. We had iterations in case of isoplanar machining to find out the forward step, but here the forward step was found out without iterations, and it was expressed as a parametric increment along the cutter path, which is expressed as a function of a third parameter t on the surface R u w. So, what do we have here? We have here this particular cutter path. Along the cutter path, this tangent has been taken at this initial point. Our target is to find out the incremental increase which will allow us to reach this point designated by parameter t 2 from parameter value t 1. So, mind you, this is the parameter value, while the curve position vector is R t 1 and R t 2 at these points respectively. This R is not the radius. This R, however, is the radius. This one by curvature. I am sorry, this might be slightly confusing, but please be alert about this particular difference. Now, whenever we are considering the tangent, first of all, let me state that here it was stated that delta t, that particular parametric increment along the cutter path expressed as R t, that particular parametric increment which will give us acceptable forward step is expressed by this expression 8 E, where E is the form tolerance, divided by the curvature minus 4 E square divided by the first fundamental form of the surface. So, what do we have here? R t, that means the the tangent along the cutter path can be expressed in a chain form. This is the complete differential. So, this is basically dr dt expressed in the in chain form, because r is basically a function of u and w, and r t dot r t, if we take the dot product of the tangent to the cutter path with itself, we have these two dot producted, and ultimately it gives rise to this expression. How do we have this? dr du, del r del u is simply expressed as r u, del r del w as r w, and when we multiply this, r u dot r u will give us E as defined before. So, this way this term will simplify to this term. It is extremely simple, straightforward. You can try it out yourself, and this is nothing but the first fundamental form that we had previously defined, and therefore, we equate this to I. So, that R t, this is the dot product. So, it basically it will involve the square of the magnitude, therefore, the absolute value magnitude of R t is nothing but root over first fundamental form, and after getting an expression of this R t, what we do is we bring in Pythagoras theorem, where r square minus r minus e square must be equal to this side square. This is expressed here, and we express this particular distance as nothing but r t delta t. Therefore, half of it is equal to r t into delta t by 2, okay, because r t is basically dr dt into delta t will give us this complete distance, assuming that this particular angle is so small that it can be well considered to be in the direction of the tangent. From this one, we can easily simplify. I am leaving this to you. We can easily simplify that delta t comes out to be this one. So, we are avoiding iterations and getting an expression of delta t, increment of parameter along the cutter path, in order to give acceptable forward step. So, after this we come to the side step. How is side step taken in case of isoscallop? One method could be, once we see one existing cutter path moving this way, and there are forward step approximated or points calculated as per forward step, their locations are already determined. That means, these small blue circles are the positions at which, if the tool is placed, it will give us acceptable forward steps. That part is done. Then we are trying to find out the positions of the cutter path, cutter contact points on the potential cutter path by the side of it, which has not been found out up till now. We are trying to calculate the positions on this particular cutter path, which will give us acceptable side step. For this, what we do is, we say that okay, this particular step that we have to take, it is definitely going to be defined by a vector. We simply find out its direction and magnitude, which is all there is to it for a vector. So, what we say is, let us first find out in which direction we should consider the side step at this particular location of the cutter position on the first cutter path. So, on the first cutter path, if we look at it at this position, the tangent to this cutter path, which is basically once again that r t, that gives us this particular tangent, gives us the direction of the cutter along this cutter path at this point. We will take the side step at a direction perpendicular to it. So, we will say that tangential direction on the surface at this point, making a 90 degree with the cutter, sorry, making 90 degrees with a cutter tangent. Okay. That particular tangential direction will mark the direction of the side step. So, what we say is, I am sorry, suddenly R has been replaced by P by mistake and V has been replaced by W has been replaced by V. Please understand that this basically represents nothing else but the tangent. That means, please read it as del R del U into du dt plus del R del W into dw dt. Okay. Nothing else. This expression of general tangent we have come across. So, what we are trying to establish here is that there are basically two tangents that we are considering and they are dot producted to give us a 0, which means they are mutually orthogonal. That means, they are perpendicular to each other. One tangent is already the existing tangent in the cutter path direction and the other tangent we do not know about it, we are going to solve for it. So, this is the relation that defines the orthogonality of cutter path and side step directions. Okay. Here it is interesting to note that this expression represents the tangent along the cutter path and R u and R w they are figuring here. And in this one also R u, this should be R u and R w, they are also figuring here. Why? Because R u and R w they are invariant, they do not depend upon the direction. Du dt, dw dt etc., these will be these will be dependent upon the direction in which the tangent is being considered. So, from the previous expression, the dot product, we will ultimately have dw by du. If we can cancel out the dt terms, dw by du giving the direction of the tangent in the side step direction to be this one. So, it is related to first of all the surface constants and it is also related to the direction of the cutter path. dv du should be actually dw du. This is related to the cutter path direction at that particular point. So, after having established this one, that is, we now know the direction in which the cutter side step has to be taken. We are trying to establish the magnitude, how much should be the cutter side step magnitude. For that, we take the help of simple geometry and we say that if the surface be convex, there will be two positions of the cutter on adjacent cutter paths. Okay. These are side by side on separate cutter paths and this is the small amount of material left behind uncut, and P x determines denotes the height of the scallop. Okay. It is written here P x is equal to scallop height, A b is equal to distance between centers. Obviously, these are the centers of the two positions of the cutter round nose and we are calling it twice A, and the side step however, is the distance between the two cutter contact points at L and M, and therefore, L m denotes the side step. So, what we are going to establish from here is that since these will be ultimately meeting at the center of the center of curvature of the surface, therefore, we have similar triangles in which L m divided by A b will be equal to radius of curvature of the surface divided by radius of curvature of the cutter plus radius of curvature of the surface. This we have written down later on, or we can quickly write it down here on the on paper. That is, if we have two positions of the cutter here and if this be the surface, this be the first line, I mean the normals containing the radius of curvatures. So, we are basically saying this is if this be the side step and if this be the center distance and if this be big R, the radius of curvature of the surface orthogonal to the cutter path, and this is the radius of curvature of the cutter. We can say r plus r center distance divided by side step must be equal to r plus r divided by r. This is what we are establishing. That means, we are establishing a relationship between the side step and the center distance. Why are we doing this? Because ultimately, we have to establish how much is this particular magnitude. This magnitude, once we establish, we will say that we have got the complete information about the side step vector. Its direction is already established. If I know this particular magnitude, I can say that yes, I know how much distance I have to shift in order to get the side step, which will give me a definite scallop height. This is the scallop height. Okay. So, coming back to the figure, this from this particular figure, it is possible to calculate the scallop height by a few Pythagorean relationships. Let us see that. If we have this calculation carried out, I am not going through the calculation, but I will just point out one or two of them. What we can say is that here there will be one right angle triangle x d b. So, that we can say x b, which is nothing but the radius of the cutter square must be equal to x d square plus d b square. D b happens to be half the center distance. So, that we can induct center distance into the calculation with cutter radius and this particular distance x d. X d will also be related to the cutter height, I mean the scallop height and the radius of the surface, I mean radius of curvature of the surface in a direction perpendicular to the cutter path. So, this way these relations are drawn up. It is taken from this particular reference, and I am not going through them in detail, but you can definitely follow it, and this is the relation which is coming from the geometric similarity triangular similarity relationship we visited just now, and from there this A value can be replaced here in terms of small r, big R, that means the radius of curvature of the surface, and E. Okay. So, this relation is containing A inside, so that it can be iteratively solved, or separation of variables can also be done. So, that E can be solved completely in terms of these particular parameters h, big R and small r. Once we replace this, we get an expression of side step, which comes out to be a function of these three things: small r, radius of the cutter, radius of curvature of the surface, and scallop height. So, if we specify a definite scallop height for a particular tool and surface combination, we can find out the side step magnitude at any point on the surface. Once we establish that, last of all we introduce one expression, that is the side step, the current side step position being P, and the final side step position, I mean the current tool position being P, the side stepped position of the tool being P star. Their difference can be expressed as a Taylor series expansion involving only the first derivative as P u dot delta u star plus P, please read this as P w plus delta w star. So, in this Taylor series expansion, ultimately we will get the solution of delta u and delta w, giving us the parametric increments from the present position of the cutter to the side stepped position of the cutter, which will yield the recommended value of surface roughness. This is one equation, and the other equation, if you kindly remember, was the equation that we got from what do you call it, just one moment. Oh, this is not responding. Okay, we will visit this slightly later, or shall I start this from the beginning? Please bear with me. Yeah. This was the one expression that we got for delta W and delta U. This is one equation, and the other equation we visited just now, this one. Okay. Here we put the magnitude of the side step, because P star minus P is equal to side step, and that is equated to delta U and delta V expression. So, we get two equations, these are simple simultaneous equations, and we can solve for delta U and delta W. Once we solve this, we get the magnitude, we have also got the direction, and we can pinpoint the side stepped positions. We pass a curve through this in the UV plane, UW plane, and once we pass a curve through it, we truncate it or extend it in order to start and stop at the edges of the surface. Okay. You might wonder about the fact, why is this curve through all these cutter contact points done on the UW plane and not on the XYZ plane. Please think about this. Now, we will look at another method of cutter path generation for curved surfaces following the iso scalloped strategy, in which it was observed that the cutter paths generated by the method that we had discussed and some other methods, they have two dimensional considerations of geometries, which may bring in some errors. So, we start this discussion pictorially, without resorting to those formulae and equations. This is the free form surface, and say this is a cutter path. So, this has been taken by a paper by Feng and Lee, which came out in 2002. So, this cutter path, to start with, we mark at particular points which are forward step adjusted. We determine the surface normals at these points. These points are the CL points, the centers of the nose portion of those ball end milling cutters. We join them by a smooth curve. We find out the tangents to this smooth curve, hence we get the cutter directions at these respective locations. Next, we draw the swept sections of the cutter ball end at these respective locations, and swept sections are the ones which define the geometry of the groove being cut. We remove all the construction lines. Next, we find out the intersections of the swept sections of the cutter with a surface offset from the design surface by the scallop height. So, this surface is away from the design surface, normal to it at all those respective positions by the scallop height, and this way we are determining the tips of the scallop curve at these locations on the swept sections of the cutter. So, these mark the tips of the scallop, the whole scallop geometry all through these particular positions by the side of the first cutter path. Next, we remove the scallop offset surface. We pass a smooth curve through these scallop tip points. We find out the adjacent position of the cutter in the adjacent cutter path from the consideration that it has to touch the surface and it also has to pass through the scallop points which are already determined, and there is another condition, that is the scallop tangent. The scallop tangent means those tangents which are tangential to the scallop curve. The scallop tangent has to be perpendicular to the radius vectors of the swept sections of the second cutter path. Okay. So, applying this condition, we understand that the scallop tangent, which is not drawn in the figure, but the scallop tangent has to be perpendicular to the radius vector of the swept sections of the first as well as the second cutter paths. Does this make the consideration that these two swept sections will be coplanar? No. While the radius vectors of those swept sections with the scallop tangent will be perpendicular, the swept sections themselves do not have to be perpendicular to this scallop tangent. We have shown one scallop tangent here. We have shown one scallop tangent here, and we are claiming that it is perpendicular to the swept tube. Okay, sorry, it is tangential to the swept tube, and therefore, it is perpendicular to the radius vector which is connecting this scallop point with the center. It is perpendicular to this particular radial line, it is perpendicular to this particular radial line, but it is not perpendicular to these planes. Had it been perpendicular to those planes, it would have again become the case of two swept sections being on the same plane, and two dimensional geometrical calculations could have been applicable, but it is not so. This is the difference of this particular model with the previous one. So, at the end of this discussion, we come to three examples of jobs which have been cut with different forward steps and different side steps. As you can well identify, this one has large forward steps and also a very coarse side step pattern, so that roughness will be visible to the naked eye, while these are not so. A closer look perhaps, yes. So, you can see roughly those roughness marks appearing on the surface of this body, yet closer look, yes, those are the roughness marks which appear. Now, what is the current status of CNC? Is it restricted to all these machines, machining and 3-axis or 5-axis maybe, etc.? There are different fields of application developing over time for CNC. We have CNC being applied in case of say rapid prototyping, where the whole technology of rapid prototyping is dependent upon CNC. Unless the movements of the machine can be precisely controlled, I mean the different slide movements, different stages, we cannot have the implementation of different technologies, as I discussed, for example, rapid prototyping, and that way CNC dependent technology is developing very fast, and ultimately it will move on to different other fields. For example, in middle level production, we are having flexible manufacturing systems, which is basically computer controlled, and only in mass production we have special purpose machines. There are other aspects of machining in which we have copying of different geometries. Still, there also we are gradually having the development of technology which can work without part specific tooling. Part specific tooling means basically tools which are dedicated to specific parts, and that way we are very much dependent upon special tooling, physical devices, etc. and CNC is targeted towards elimination of such technology. Thank you.